Let's see if we can gain a little more insight into the behavior of the LRC series circuit by doing a little graphing exercise. So here we're given an LRC series circuit. The inductor, resistor, and capacitor are all in series with a generator. We could replace the symbol capital V with capital E, so we can think of the voltage as an EMF. Anyhow, we know that the current varies sinusoidally in circuits like this, and we're told that the current can be given as the function says instantaneous current, lowercase I, equals maximum current, capital I, times cosine omega t. Now here, the omega is given a subscript d. You can write that if you want to. That's just so we don't confuse the driving frequency. That's what the d refers to here. We don't confuse the frequency that the generator is driving the circuit at, so to speak, with a different frequency, omega naught, which represents a resonant frequency. Now, sometimes the driving frequency is the resonant frequency, and then the circuit behaves in a very particular way. But in general, the driving frequency can be any value you want, whereas the resonant frequency is entirely dependent on the values of the capacitance and the inductance. So resonant frequency is always equal to 1 over the square root of LC, whereas driving frequency, well, it's up to you. You can drive the circuit at any frequency you want if you have a generator that has a variable frequency knob on it. So let's get to this problem. We're told that we have an equation for the current. That means the voltage at any instant across the resistor should be equal to resistance times the maximum current value, and then also times cosine omega t. We say that the voltage across the resistor is always in phase with the current, and this graph shows how the voltage across the resistor is varying in time. So let's put an origin in time on our axis, because this is a graph of cosine, and I suppose a line that cuts right through there represents the y-axis, right? The axis upon which we're labeling the voltage on the resistor. So there's time equals 0, and then you can see our graph corresponds to a graph of cosine. It also said, notice that the maximum value of the voltage is 3.3 volts. So I suppose that means every line on the graph paper is worth 1 volt. Let's see, there's 1, 2, 3, yeah. The peak value would correspond to about 3.3 volts, so that looks good. So here's our instructions. We have to use a blue pen. Let me switch over. Okay, so I got my blue pen selected. We're told to make a graph of the voltage across the inductor on the same set of axes and make an assumption that the maximum value of voltage across the inductor is only going to be 1 volt as opposed to the resistor's maximum voltage of 3.3 volts. Okay, well, that's doable. I'm going to keep in mind this mnemonic, Eli the Iceman. And in particular, the Eli part of it. This is just telling me that EMF, or voltage, comes before current for an inductor. So let's look at it this way. At time t equals 0, the voltage across the resistor is at its greatest value, and a quarter cycle later, that voltage goes to 0. Well, let me pick a different color so I don't confuse. The blue is supposed to just be for the inductor. Okay, so how about we go with bright pink here. Yeah, there we go. So sure, the voltage across the resistor after a quarter cycle drops from its maximum value down to a value of 0. And then another quarter cycle later, so total a half cycle from time t equals 0 later. Now the voltage across the resistor has a maximum magnitude but negative, right? It's reverse polarity. 3/4 of a cycle, it's back to 0, and in a full cycle, it returns to its maximum value. Whatever is happening to the resistor, that same thing should happen to the inductor, but should happen earlier. The voltage across the inductor should reach its peak value a quarter cycle before the voltage across the resistor reaches its peak value. So we've got the dead giveaway here. Let's find where the voltage across the resistor has reached a peak value there. So let's go earlier in time, 1/4 cycle, so like corresponding to this point. That's when the inductor should have its greatest value, and it's only of 1 volt. So here we go. We should have a graph that reaches a maximum value of 1 volt at this instant in time. And then if we look back at the resistor, it goes from a maximum value at this point in time to a value of 0. Well, the inductor was a little bit ahead of the game on that one. And so it already had its maximum value here. So by the time the voltage across the resistor is at its maximum value, the voltage across the inductor has already reached its 0 value. Now for the resistor, a 1/4 cycle later, it's going to reach the most negative value, but for the inductor, it beat it to the punch. It was already there. And so when the voltage across the resistor was 0, the voltage across the inductor has already reached its most negative value. And so this process goes on and on. Whenever the voltage across the resistor has a value that's reached a peak, either positive or negative, those are going to be the moments in time that the voltage across the inductor is 0. And so we can see in this graph that the voltage across the inductor is leading the voltage across the resistor by 90 degrees. So maybe you get a better sense of what we mean when we refer to this mnemonic, Eli the Iceman. So there we go. This kind of looks like a graph of negative sign, right? So there we have it. One graph shows the voltage across the resistor, and the other one we've drawn in blue is the voltage across the inductor. Switching over to red, use a red pen to draw in the voltage across the capacitor. So let's put our time axis in once again. That orange line represents our origin in time, t equals 0. And we can also see that the values have stayed the same. There's 1 volt, 2 volts, 3 volt, so on. Okay. Well, Eli the Iceman. Let's look at this part. Ice, Eli the Iceman. Current comes before voltage for a capacitor. Or in other words, the voltage comes after the current. So think about it like this. Whatever the voltage across the resistor is, so that's the graph that's already shown, right? This one I'm highlighting in pink, that's the voltage across the resistor. But that's the same thing as the way in which the current is cycling, because voltage across the resistor and the current are always in phase. In our example, they're both given as sinusoidal functions expressed by positive cosine. So when I say the voltage across the capacitor leads the current, it's just as well to say the voltage across the capacitor, the voltage across the capacitor lags the current. So the voltage across the capacitor, or the voltage across the capacitor, lags behind the voltage across the resistor. All right. Hopefully you understand what I'm saying with that. You'll see it in the graph. Let's look at this point in time right here. So the current has reached its maximum value, and therefore the voltage across the resistor has reached its maximum value. And a 1/4 cycle later, it's going to go to 0. Well, the capacitor is a bit behind the times. It takes time for charge to build up. So as long as the value of current is positive, the capacitor is still charging. So at the moment in time that the voltage across the resistor reaches 0, that's when the voltage across the capacitor finally has its max value. And we're just given an example. We say assume that the greatest voltage across the capacitor is 2 volts. So here we go. 2 volts right there. There's a data point. When the voltage across the resistor is 0, that's when the voltage across the capacitor is either going to be a minimum or a maximum value. And vice versa, whenever the voltage across the resistor is maximum or minimum, that's when the voltage across the capacitor is going to be 0. So I'm just going to put in a bunch of data points. So here's a point in time when the voltage across the resistor is a maximum, then I know that's when the voltage across the capacitor will be 0. Voltage across the resistor is a minimum, so voltage across the capacitor will be a 0. So I'm putting in all of my 0 points as red dots here. That part's easy. And then I just have to keep in mind that the voltage across the capacitor lags behind the current. So if I can find the places where the voltage across the resistor has reached its peak value, the voltage across the capacitor will reach its peak value just a little bit later in time. So where there's a 0 value here for the voltage across the resistor, that's when there's the greatest voltage across the capacitor. So there's one of these data points. Here's another one of these data points. So you can see that every time the voltage across the capacitor is maximum, the voltage across the resistor at that instant is 0. So if I can find all the zeros for the voltage across the resistor, then that has to correspond to either a maximum or minimum value of voltage for the capacitor. So this one corresponds to a maximum, so this one's going to correspond to a minimum. There's another minimum, so on and so forth. Here's another minimum. If I connect all these points together, we get a graph for the voltage across the capacitor that's also sinusoidal. It shares the same frequency as the voltage across the resistor, but it's just shifted a little bit later in time. Eli the Iceman. So finally, we're asked to put it all together. So let's find all the zeros. Well, first of all, put on our origin for time. There we go. Label the given graph. So this graph here is the voltage across the resistor. Find all the zeros. There's one. There's another. Yeah, this part's easy. Wherever there's a 0 for the voltage across the resistor, that's when the voltage across the inductor or the capacitor are going to have their maximum or minimum values. And the phase relationship between voltages for the inductor and the capacitor are 180 degrees out of phase with one another. So the voltage across the resistor and the voltage across the inductor are 90 degrees out of phase. The voltage across the resistor and the voltage across the capacitor, and this is a case where the voltage across the capacitor is greater than the voltage across the inductor. In our example problem, this is 1 volt. This is 2 volts. And I should draw this a little longer. This one is 3.3 volts. Right, that would be a phasor diagram for this one. So, the phase relationship between the voltage across the inductor and the voltage across the capacitor is a full 180 degrees out of phase, half a cycle. So when one is max, the other is min, and vice versa, but they both have their zeros at the same moment in time. So in blue, here comes our graph for the voltage across the inductor. It always leads the current by 90 degrees. So this 0 for the voltage across the resistor is when the voltage across the inductor is maximum. There's a 0. There's a 0. Here's a minimum, a 0, a maximum, a 0, a minimum, a 0, and a maximum, and so on. So I think I have enough data points that I can trace in this graph. And there we have it. The voltage across the inductor has a peak value of 1 volt, and is definitely leading the behavior of the resistor by 90 degrees by a quarter cycle. So let's draw in the behavior for the capacitor. Well, it shares its zeros with the voltage across the inductor, and then it's 180 degrees out of phase. So when the voltage across the inductor is the most, the voltage across the capacitor is the least, and vice versa. In our example, that's a 2-volt value. Okay, so there's another one. There's another one here. And another one here. I think that's enough data points to fill in my graph. There we have it. So that's good enough for us to see how all the values are cycling together. Let's label each one of these. There's the voltage across the capacitor. And here's the voltage across the inductor. Now we're given a challenge using orange. Draw the sum of all 3 voltages at any given moment in time. Well, let's try something. Let's answer this next question. What's the peak value of the overall EMF? And does it reach its peak before or after the voltage across the resistor is reaching its peak value? Let's look into this. The overall EMF, I guess if I draw this phasor diagram once again, I got to keep the voltage across the resistor as 3.3 volts. But I can combine 2 volts in this direction with 1 volt in this direction is just as good as having 1 volt this way. So using the parallelogram method for vector addition, finding a resultant, this just follows from the Pythagorean theorem. So in other words, the EMF is the square root of the voltage across the resistor squared plus the difference between the voltage across the inductor and the voltage across the capacitor. So this is the square root of 3.3 squared plus 1 minus 2. Well, that's going to give you a negative 1, but anything squared is still a positive value. So grab your calculator, see what you get. 3.3 squared plus, well, 1 squared is 1. So what you should have is the square root of 11.89, which comes out to about 3.45 volts. Okay, let's look at another equation we have. The tangent of the phase angle is equal to the voltage across the inductor minus the voltage across the capacitor divided by the voltage across the resistor. So we have, once again, 1 minus 2 divided by 3.3. What's the inverse tangent of that? That'll give us our phase angle. So this is the inverse tangent of a negative value. So this is inverse tangent of negative 0.30303, on and on. And that gives us a phase angle of negative roughly 16.9 degrees. Okay, so when the phase angle is negative, that means that the driving frequency is below the resonant frequency. If the phase angle had been positive, that means our driving frequency is greater than the resonant frequency. And of course, if the phase angle equals 0, then that means the driving frequency is the resonant frequency. So situations like this, where the driving frequency is below resonance and the phase angle is negative, we can say the circuit is behaving capacitively, which guarantees us that the maximum voltage across the capacitor is greater than the maximum voltage across the inductor. When you have positive phase angles by driving a circuit above the resonant frequency, then we say the circuit is behaving inductively, and that's a guarantee that the maximum voltage across the inductor is greater than the maximum voltage across the capacitor. Well, that's certainly not what we have in our example problem, and you can probably figure out what it means to drive a circuit exactly at the resonant frequency. So we have an expectation for the answer here. We know the value. What's the peak value of the net EMF? It's 3.45 volts. In other words, the length of this resultant vector here is like a hypotenuse of a right triangle. We have a length of 3.3 on one side, a length of 1 on the other side, so that corresponds to a hypotenuse with a length of 3.45. So that is the voltage, peak voltage of our generator. This is a 3.45 max. Now if you want to know the RMS value for the generator, then you'd have to do 2 over pi multiplied by 3.45. Oh, I'm sorry. That's how we would get the rectified average value. If we want the RMS value, it's 1 over rad 2 times 3.45. I misspoke. Okay. So let's see if we can draw this in. Because the phase angle is negative, then I know this 3.45 voltage comes a little bit later in time. The voltage from the generator is lagging behind the voltage across the resistor. So I guess the angle from, let's pick 2 points. From there to there is an angle of 360 degrees. That's a full cycle. So from here to here would be an angle of 180 degrees. That's half a cycle. And then, my goodness, from here to here, that's a quarter cycle. That's an angle of 90 degrees. So just by scale, just getting a rough sense of it, 16.5 degrees might be represented by, I don't know, about that far or something. So I expect to have a value of 1, 2, 3, let's see, that's 4. So 3.45 would be about here, okay. So there, I expect to have a maximum voltage across the whole load at that instant in time. So all we really need to do is make a graph that's sinusoidal with the same frequency as any of our 3 graphs. Each one reaches its peak at a different moment in time, but they all have the same frequency as one another. They're just shifted in time. So the same thing with the overall output. So I just need to make a sinusoidal graph that comes about 16.5 degrees later and has a slightly higher max value. Instead of 3.3 is 3.45. So here we go. Yeah, I got this. I'm going to make it a little more bold here. Yeah. That's the stuff. I would suppose a graph something along these lines represents the overall voltage of the whole load. Okay? Now if we look at any given instant time, does this agree? Well, let's see. So let's just pick, let's pick this instant in time right here. So the voltage across the capacitor is positive at that moment in time. The voltage across the inductor is negative. However, it's not as negative as the capacitor's voltage is positive. So the net value between the capacitor's voltage at this instant in time and the inductor's voltage is positive, which adds with the value of the voltage across the resistor at that moment in time, and all those values would add up to be that great. If you pick any moment in time, by Kirchhoff's loop rule, the instantaneous EMF off the generator has to be equal to the instantaneous value of the voltage across the resistor plus the instantaneous value of the voltage across the inductor plus the instantaneous value of the voltage across the capacitor. That's just Kirchhoff's loop rule. However, it would be incorrect to say that the maximum EMF from the generator is equal to the maximum voltage of the resistor plus the maximum voltage of the inductor plus the maximum voltage of the capacitor, because we notice they don't reach their maximum values at the same instant in time, and so we can't add the max values together. So Bottom statement false, top statement true. Hopefully this gives you a little more insight into the oscillatory behavior of these RLC circuits. We'll see some more examples before we move on to our study of power in the LRC circuit.